In this video, we give an overview of the multimodal GenAI capabilities of Modalics. Modalics is SiMa's second-generation machine learning system on a chip, or MLSoC. This chip, which is about the size of a quarter, runs large language models and large multimodal models at the embedded edge with low latency and low power consumption. GenAI support is fully integrated into the Palette SDK. This means that given a GenAI model, the SDK automatically compiles the model into binaries, then deploys these binaries onto the dev kit for execution. Both the Whisper Small speech-to-text model and the Piper text-to-speech model execute on the MLSoC. As a result, Modalics enables natural conversational AI at the embedded edge at low power. Today, a variety of Llama and Gemma models from Hugging Face are fully integrated into the Palette SDK. Here are some of the Llama models that are supported by the SDK. And here are some of the Gemma models that are also supported. For each of these models, the Palette SDK automatically compiles the model into multiple binary files, then deploys these binaries onto the Modalics dev kit for execution. The Palette SDK also supports the fast loading of compiled binaries from an attached NVMe drive. While a model's performance will be maximized if all of the compiled binaries reside entirely in DRAM, the ability to quickly load binaries from NVMe enables Modalics to support GenAI models that do not fit entirely in DRAM, for example, Llama 3.1 70B. Applications of conversational AI include in-vehicle infotainment systems and humanoid robots. For example, imagine driving around and asking your car to tell you in real time about an interesting-looking building that you see out the window. The minimum token generation throughput required for an effective conversational AI experience is 3.5 tokens per second. The performance of GenAI models on Modalics consistently exceeds this conversational AI requirement. For the Llama 7B large language model, which has 7 billion parameters, the time to first token is 0.5 seconds, and the token generation throughput is 6.8 tokens per second. For the Llama 7B large multimodal model, which also has 7 billion parameters, the time to first token is 2.5 seconds, and the token generation throughput is 6.8 tokens per second. And for the tiny Llama large multimodal model, which has 1.4 billion parameters, the time to first token is 0.5 seconds, and the token generation throughput is 13 tokens per second. In conclusion, the ability of Modalics to support real-time conversational AI with a sub-15-watt system power budget is unique in the embedded edge industry. In the future, we plan to further improve the time to first token and token generation throughput metrics by implementing 4-bit block quantization for the model parameters. Model parameters are currently stored in 8-bit precision, so we expect 4-bit quantization to significantly reduce the amount of time it takes to load the parameters from DRAM into the on-chip memory. Block quantization will ensure that moving from 8-bit to 4-bit precision will result in little to no loss in accuracy. We also intend to improve model performance by implementing advanced algorithms such as speculative decoding. We will now demonstrate the conversational AI capabilities of Modalics as it runs the tiny Llama large multimodal model. This particular LMM has 1.4 billion parameters. We will first demonstrate the scene analysis use case. Before we demonstrate the ability of Modalics to perform scene analysis on an image, observe that the tiny Llama LMM is able to generate responses in a variety of languages. We will configure the system to respond in English, and we will upload an image that we would like the system to analyze. A transformer model called CLIP that runs on Modalics will first convert this image into 576 tokens. These tokens will then be processed in batch by the tiny Llama model. thus resulting in a sub-second time to first token. Tiny lava will then generate new tokens one at a time. These tokens will be converted into words and fed to the Piper text-to-speech model that also runs on Modalics.
Let me think about it. The image features a large, old church with a steeple and a clock tower. The church is surrounded by a grassy area, and there are several people walking around the area. Some of the people are closer to the church, while others are further away. The church is situated in a park-like setting, with trees and a bench visible in the background. The overall atmosphere of the scene is serene and peaceful.
We will now demonstrate the ability of Modalics to process text-only queries. The Whisper-Small speech-to-text model that runs on Modalics will first convert the speech prompt to text. The text will then be converted into a sequence of tokens and passed to the Tiny Lava model. Tiny Lava will then generate new tokens one at a time. These tokens will be converted into words and fed to the Piper text-to-speech model. Why does Jupiter have a big red spot?
Just a second while I think about it. Jupiter has a big red spot because it is a large, dark, and irregularly shaped object in its atmosphere. The spot is caused by the presence of a large amount of sulfur dioxide gas, which is a common component of the planet's atmosphere. The sulfur dioxide gas is released by the planet's atmosphere, and over time, it can build up in the form of a dark spot. The spot can also be caused by other factors, such as the presence of a large amount of water vapor or other gases.
This concludes the Tiny Lava demo.